Okay, so at RNAO, well, actually, first, everybody's probably really tired. It's like 9 o'clock. Everybody stand up. Stand up. I know you're all tired. You know, ready to go home. Put your arms up. Stretch out. Take a deep breath. All right, sit back down. Cool. Maybe you'll pay attention. I don't know. So we're building queues on RocksDB. You should probably never build queues on disk. It's a terrible idea. Like, don't. Why would you ever do this thing? But people will pay you money for this thing, so we're building these things if you need that kind of thing. So who am I? You've probably never heard of me. So this is the slide, obligatory. I go to these tech talks. Everybody has a slide. Who are you? I was just an undergrad at Auburn, so you've probably never heard of me, which is good. I would be really scared if you did. So far, there's pretty much no reason to listen to anything that I have to say, but feel free. So now we got that out of the way. Here's the obligatory formidable pictures from my childhood. You should all be really, look at this guy. So why would you ever want to write queues on disk? Like, what? So some people don't like it when you throw all these things on the floor. So you go run RabbitMQ. They're going to drop everything on the floor as soon as they have a partition. So some people aren't really big fans of that. So we're trying to build a queuing system where we're not going to throw anything on the floor, even during failures. So the whole data center shuts off and comes back online. Your messages are all still there. You weren't able to write. You probably sent me a lot of emails being very mad about not being able to write, but you didn't lose any messages. So this is how I feel about this situation. It's somewhat infuriating, and I'm very innocent, and I have no idea. So here, we'll give you a basic queue terminology, just in case you haven't dealt with message queues at a really low level. So if you enqueue, pretty simple, you put a message onto a queue. You want to guarantee some kind of ordering to where it won't be the first thing that you pull off of this queue. Dequeue is where you pull a message off of a queue, but in a message queuing system, you don't want to delete that queue because people want to process that message, and they might actually not successfully process that message, in which case they want the message to go back on the queue so that another process can actually process the message. So we'll give you the message. It's going to hang around for a little while, and then you can ACK or delete, and we yank the message off the queue. And so there's some interesting deletion semantics in message queues if you've ever played with these before. But timeout is where we say if you dequeued a message, we never received an ACK for it, it's going to go back onto the queue. So that's pretty important so that we don't just drop all your messages. And then for counting, since we have this really fucked up thing where we have timestamps, we can't just say tail minus head and that's your queue size. We can't just be like, it's just the tail minus the head. There's a difference there, and that's how many messages you have on your queue. Or we can't just go count each individual thing because you might have a billion messages on your queue. So we don't want to go over S order n to count all those. We don't want to do the stream thing where, like hyperlog, where they'll just take a wild guess at how many things you have on there. And then you're like, oh, I have -10 messages. Well, I'm done here. So we try to give pretty reasonable counts. And that's actually super challenging to do. It's probably harder than doing the actual messages. We should probably just say oh, you have 1,000 messages. But so let's talk about how we got to RocksDB, because I think that's probably generally what this crowd is interested in. So these are my really terrible rocks puns, as I promised. So MongoDB is where we started. I think we all have feelings towards MongoDB. Maybe we should sit around and talk in a little circle and pass a pillow around, get some of these feelings off our chest. I don't like it either. So turns out it doesn't scale, as we know. It just they lied. We're kind of angry about the situation. There's really nothing we can do about it except for find alternatives. So we have we had all these fucked up things for how we simulate queues on MongoDB, because they have this global database lock where you can't actually do anything while you're writing this thing to this other thing, and you've got this other thing over here that has nothing to do with this thing, but you can't touch your thing because somebody's touching anything. Just like, why? Like, you know, like, please, let me just touch my thing. So, we had message windows so that we built an entire lock service, external completely to Mongo, so that we could do our own locking, because Mongo doesn't know how to lock very well. Clearly, those guys just never really read anything on any of that. So we have these windows where you say, like, oh, okay, I've got 0 to 100 messages. And so you've got the next 100 to 200, right? So we have this general ordering of message windows, right? But, you know, you go, say you clear out, like, window 1 except for message number 55. And then you have window 2, and you forget to pull off number 75. So then we have all these windows that you're going to have to pull from MongoDB. You get this match, or you get this batch from Mongo. You're like, oh, you have to go iterate over all these things. So be like, oh, okay, I need this guy. And then I'm like, oh, I need another window because you asked for 50 messages. So I'm going to go over 500 different windows just to find your 50 messages. And I hate MongoDB, and we just need to get off of this thing. So we have networks that we have to span, and there's this whole thing about, like, Byzantine generals that are surrounding this thing, and we don't really want to talk to the Byzantine generals because some of them might be lying to us, and sometimes we have network latencies, and Amazon decides that they want to partition us, and it's all these really just messed up. It's a messed up world. So we don't want to go across any network. We just want to have it locally, or not have it locally, and we can just go talk to our friend. So let's get off this thing. So this was horrible, right? This is pathetic. I could probably, like, hand you messages this fast. So we're like, oh, we'll try this LevelDB thing. Like, Google made it. Google's smart people. We'll go try this thing out, right? So we did. It gives us all this. We don't have any message windows. We don't have to go through, like, all these weird batching things. We don't have this weird locking service. It's always, like, dying on us when we can't get any locks. So we don't have to worry about this whole external process at all. And we have no like, Byzantine generals that are lying to us, or we don't have anybody who's, like, we don't have any false network partitions, and we don't have to worry about this provider who can't decide which shard key we want to use. Okay, my GIFs aren't working. I'm really angry. This is a really funny GIF. Okay, I'll get over it. So then we decided, this is great, this is beautiful. We've got this one process we can just run on a machine, right? It does everything we want it. We don't have to run all these lock services or anything. So so this is what happened. So you know, if you test anything, you should test it in production, right? Hey man, why can't I get any messages? Like, for 2 minutes, we're just I log on. What's going on here? Well, it's compacting. Why have we been compacting for 5 minutes? I don't know. So the CPU is not doing anything. We have 32 of them. It's kind of fucked up. So this is my other GIF that is not moving. Really, I worked really hard to find these GIFs. Okay, so this is Mark. This is Mark saying "fuck." So just build a picture in your head. It's pretty funny. Okay, so now what are we gonna do about it? So we were like, LevelDB, pretty good, right? If we could just dig in, we could figure out what was wrong. We could fix it. We could, maybe we compact in 2 threads, stuff like that. So, are we gonna fork it? We have like 5 people working on this thing, and we're constantly getting yelled at by customers. No, probably not. So that's probably not gonna happen. So. we found a fork, found RocksDB, which is awesome. Thank you guys. And we had all these knobs to turn. Got all these sleepless nights that I could have. So, yeah, previously we had nothing. So, which ones do we work with here? Nobody knows where we're going. So, right stalls, better. So we hadn't really tuned very much yet, but initially we were like, throughput went way up, latency was down. So now we go back to Java land, and we have this, I don't even know how many chars that is. I should have counted. But yeah, I don't want to say that. I might run out of breath and just collapse. It's not your guys' fault, but, so, deep breath. So we were getting 4,000 messages per second per queue, and that's because obviously we have to have some kind of serializability. So yeah, it's not bad, but wait, there's more. So now we have all these knobs. So we looked at what was happening, and we're like, we have all this variance for dequeues. So enqueue is great, like we can just write everything, but as soon as you want to get a message, like, we're going to go up to like 10 milliseconds. And we're going to go back down to less than 1 millisecond. And we're going to go up to like 100 milliseconds. So it's kind of like, what's happening here? Like, we're calling the same operations every single time. Like, why are these changing for a very constant workload? So what we found was tombstones. I hope you get this movie reference. It's a great film. It's really long. It's way worth it. You'll learn a lot about life and love and all that stuff. So here's what changed. So previously it was like, I want to get a message off a queue, right? I'll just get the head of the queue. It's super simple. Like everybody knows how to do this. So when you try to get the head every time, it turns out like any of these log structure merge trees aren't actually going to kill the head. So they're just going to say like, oh, I'm going to put a little 1 here, and I'm never going to give you this key again. So we just had like thousands of little keys that had 1s on them. We're like, oh, you have 1, you have 1, you have 1. So we can't touch any of these things. And so we're just going to go, it was like order of, whatever, seeking through God knows what to find some key that had a 0 on it. So we're like, oh, it's pretty simple. We'll just like keep track of the head, right? Which is stupid. We're probably like, it's really hard to actually do this because you could have messages that aren't available and you have to insert them to the front of the queue. So we have to make all these checks now, but it's way worth it because dequeue latency went way down. So the seeks, kind of expensive, but the seeks are kind of worth it once we actually can keep track of where we are. So now we only have to go over basically one key that has been marked deleted. We just go to the last key that we deleted, and then we get the next one. And so you get pretty good performance from that. That works great. 10,000 messages per second per queue. This is pretty substantial. Latency was also much better. It was just flat. Or like, most of the time it's less than a millisecond coming out of the database. So here's more terrible pictures from my childhood. Pretty intimidating. It's a BB gun. So what is wrong? What's wrong with this? So like, we have to count everything because it turns out people really don't care if their messages are there. They only care how many messages might actually be there. So they'll yell at you if their counts aren't right to a T. So we have to like lock everything just to count, just because people will send me emails if our counts aren't correctly. So we get our write batch, we lock, we increment our size, we increment the total, and then we write. And so how many operations do we have here where we have enqueue and then we have ACK that are both doing the count? So we have, when we delete a message, we have to decrement, and when we put a message on, we have to increment. So these could be batches where that write takes forever. So like, I want to put 256K messages onto my queue. Like that write is just going to take a substantial amount of time, and we're going to have to lock down all the deletes just so that we can count, so that people won't send me emails. So This is basically what we were doing was increment, and then you byte encode the array just so that we can stick it in RocksDB, and then put it in RocksDB with all the other messages so that it's atomic. And what we did was we used the merge operator, which most people are probably familiar with. If you haven't played with it, it's super easy to use. It's really awesome. You don't have to use mutexes anymore. Makes your life better. You'll probably live longer. So now we just say 1, like, oh, you put a message on. We'll just add 1 whenever the messages actually get written to disk. So now all of our deletes can continue. We don't have to wait on all these deletes for messages that might actually time out by the time that your delete return. And then all your writes aren't serialized with one another. So like now you can do concurrent writes basically with respect to RocksDB. So we can just throw millions of writes at RocksDB because it doesn't really matter, and it's going to count them whenever they get there. So this helped performance a lot. We went up to 26,000 messages per second per queue, just because we weren't locking anything. Except for dequeue. Dequeue is linearizable. And so we did some other things, like we stopped using message pack for really dinky little things that we're putting in for queue structures, which message pack is great, but Go's garbage collector is not so great quite yet. So we started writing encodings. Anybody? So now this is kind of what we're doing. We're working on building replication on top of this. And we're pretty far along. So this would, if I talk about this, it would be very similar to what Andy just talked about. And we're doing like the same thing. We look at their repo and we're doing the exact same thing. We're kind of kicking ourselves because we were like, well, we can't wait on this thing, go work on this thing. We're already so far along with our thing. So we do gossip protocol so that we're not saturating the network on all these heartbeats, which everybody's probably read the paper on, like Swim or something. So we have, you know, traditional like op logs so that we can roll back commits if anything goes terribly wrong. RPCs, and we have proxy. So we built a proxy so that we can keep like single node application semantics. So this is kind of like our shtick, I guess. This is how we maintain performance. So we basically just stick a proxy in front of everything and shard, and we know where to send the actual HTTP request to. So we just keep the application semantics. We don't really have to change anything. We just stick this proxy in front of it, which is super convenient. So yeah, you probably heard about all that stuff. So right now, it's actually kind of like we're in a really weird state where we can't even max out RocksDB at all in our application. Our IO weight tops out like 5% during a huge compaction. So we're just like, we're not even pushing it. And we're all getting reasonably good performance for writing every message to disk. And then we're dealing with like Go's garbage collector, and malloc is evil, and there's some other little things that are just not pleasant, like message pack. So like, we're kind of, we'll get there. We'll get ridiculous throughput eventually, hopefully. But right now, it's like as fast as we can serve HTTP requests. And there's minimal, obviously there's some latency to get this message off a disk, but it's on the order of milliseconds with a lot of threads. So things look pretty good. We're really looking forward to like topping out RocksDB. Actually, we should probably just stop testing with HTTP and the whole thing so we can know. But yeah, so this is perf tools, which you guys probably all know and love. So you can see like 21% GC. The other 21% for system, that's malloc. Yeah, 17% of our time is actually doing our writes, right? We're spending 8% doing JSON. Everybody loves JSON APIs. So yeah, we're dealing with this. Like JSON makes all of our garbage, right? So we just can't get around this whole system. It's really like this fucked up world we're living in where we can't write JSON decoders. So like we don't know what we're going to do about this, but anyway, this is kind of where we are. This is the bowels, but yeah, you can see there's like minimal overhead from the actual router down to like right there, 28%. That is all this guy right here. And then like we're just spending a fifth of our time. We have like 30 cores here. They're just doing GC and they're all angry about the whole situation too. So anyway, I started writing I was like, oh, these guys will like if I wrote like this really stupid queue system that is completely useless, and then just benchmark the hell out of it. So I started doing that. I was like, I don't really think that's very interesting at all. It would be like, oh, I use this RocksDB option. And so if you're interested in that, if that really makes you happy in life, then you're welcome to go look at it. It's reasonably cool. I made this interface where you just put in whatever storage layer and you define like how to enqueue and dequeue something, and it will magically do everything else for you. And you can benchmark it and then see how much time you spend garbage collecting because Golang. So yeah, Go is awesome, but the GC thing is like, for databases, not so convenient. But anyway, I'll take questions and comments if you guys are still awake. We're running on SSDs, so yeah. On Amazon SSDs, which have variable, yeah. We're running on, like EC2 for now. We're going to run on other clouds probably. Maybe they give reasonable amount of IOPS, but I don't know. We haven't really tried it yet, so. We did look at Kafka. Kafka has some features. Yeah, so did we look at Kafka? Yes. So we did, and if I recall correctly, it is mostly in memory. No? Is that a lie? Okay. I don't know. I've looked at a million of these things, so I can't keep track of them all. They're all the same, hack, enqueue, delete. But cool. So yeah, we did, and they have some interesting features. Like the replay feature looks super interesting, but we just decided, nope. I think maybe I just was very convincing in my argument that I wanted to write one for myself. Can we go with that?
What kind of workload do you have?
So I'd say that the most popular workload is heavy enqueues, heavily concurrent enqueues from a bunch of servers. And they just splat a bunch of messages on, and then they'll have one process that just kind of pulls them off. Maybe that's just because that's how it appears. They might actually be trying to dequeue more, but the most popular thing is just an aggregator. It's just a central location to throw everything into, and then we're not going to drop everything on the floor. People like that guarantee. So that's the main one. And then we have push queues too. So people really like that because then you don't have to go pull everything. You can do fan out just through the API. So if you enqueue a message, we'll fan it out to whatever number of HTTP subscribers or another message queue or another 10 message queues. So you can do some interesting things there if you want to.
What's the latency look like when you have a large fan out in the queue?
So we had a recent optimization with this where we share the message on disk. So it's actually, it really depends on how fast your HTTP subscriber could yank it. If you're putting it on another message queue, it's basically free because we're just assigning an ID. We can all go sleep now.